If you are referring to Chengen and Bowles' book, you should be looking at chapter 14, and the title is Gas Vapor Mixtures and Air Conditioning. So both titles are interrelated. So when we want to perform a good air conditioning process, we need to understand how mixtures and how the presence of water vapor in the environment or in the atmosphere is behaving. Okay, because we are dealing with conditioning the air. So the concept of air conditioning is that we want to cool the air only, but it's actually concerned on how we control the amount of moistures in that particular volume of air. Okay. So chapter 14 in the Chengai Umbul's book. So you can refer to the thermodynamics book, and the title is Gas Vapor Mixtures and Air Conditioning. Okay, so these are the contents briefly on the atmospheric air and what are the terminologies that will be involved, and the symbols, the parameters, the units, and then we're going to have a look also on the importance of the psychometric chart and how we can use the psychometric chart to understand the quality of the atmospheric air. Or if you are talking about conditioning an enclosed room, for example, your living room or your house or your hall or wherever. So as long as we know the physical parameters of that particular volume, then we can work out what would be the cooling requirement or how we can encourage the call it the reduction of humidity, and everything is revolved on the theory of mixtures, and psychometric chart is one of the tool that enable engineers to understand on how you can manipulate the presence of moistures, and by adding or removing the water vapor in the atmospheric air, how it can affect the comfort and we call it the living condition related to the air conditioning process. And when we talk about air conditioning process, among the main processes that we consider through the psychometric chart theory is how we can conduct a simple heating process, a simple cooling. Okay, so when we say simple heating, we're talking about the delta T to increase the temperature. Simple cooling means also delta T, reduction in the temperature. And then heating with humidifications. Humidification means that we talking about the process of adding the moistures in that particular volume of atmospheric air or air, and then cooling with dehumidifications. Dehumidifications means that we want to remove the presence of water vapor, and at the same time, by removing the water vapor, how we can reduce the temperature of that particular volume of air. The chapter also follow the topic on evaporative cooling and as well as the cooling tower. So looking at here, these two main sections. Okay, so usually if you have your assessment, your final exam, sometimes the question related to this part here. You're the one sometimes only concerned about this part. Okay, so but they are interrelated, so you really need to understand how you can apply the theories to understand the physical operation. First objective is to differentiate between dry air and the atmospheric air, and then by differentiating, we also talk about how you can define the specific and relative humidity of the atmospheric air. And as usual, we need to calculate, and also how to calculate the dew point temperature of the atmospheric air. Okay, the relation between the adiabatic saturation temperature and wet bulb temperature. So when we're talking about wet bulb temperature, we're going to talk also about the dry bulb temperature reading. And the next one is we're talking about the use of psychrometric chart as a tool to determine the properties of the atmospheric air. Psychrometric or psychrometric chart. Okay. And lastly, how we apply the principle of conservation of mass and imaging to the various air conditioning process. So we begin by defining and understanding how we define the dry and atmospheric air. So usually in the exam questions, the question will normally ask about the definition of the key parameters in the topic. For example, here then you need to define what is defined as the atmospheric air and the differences. The main difference is that we talking about the water vapor. If the air of in the atmosphere contains water vapor, then we call it as the atmospheric air. If there isn't any presence of water vapor, then we call it as the dry air. So dry means that there's no water vapor involved. And as I mentioned just now, water vapor is important to humans' comfort, and it's also the core concept that is being used in the air conditioning applications. Since we are dealing with atmospheric air and also dry air, and then in thermodynamics, you concern on the enthalpy, because enthalpy is the energy that you want to make use, that you can take benefit from. Another parameter that you also investigate is the entropy. So when we deal with atmospheric air, you know now that air can have water vapor, and dry air doesn't have any water vapor. So you still need to calculate the enthalpy. So the theory suggests that if you want to calculate the enthalpy of air, you can apply the ideal gas relations. Okay, and then not only for the air but also for the water vapor. So the enthalpy for dry air is related to the specific heat at constant pressure multiplied by the temperature at that particular condition and time. And the delta enthalpy, the different enthalpy, is related to the difference in the temperature. Okay. And is acceptable that when you do some calculation, you can simply assume that the value of Cp is 1.005 kilojoule per kilogram degree Celsius, provided that the temperature range is within minus 10 degrees Celsius to 50 degrees Celsius. So one of the assumptions that you can put down in your answer script is that first you assume that if you are calculating the enthalpy of dry air, then you make the assumption that the Cp value is related to 1.005 kilojoule per kilogram degree Celsius. Then the next challenge is for you to determine what is the temperature. If you're talking about the atmospheric air, and as the definition above says, that atmospheric air disclose the presence of water vapor, then when you write down the pressure for the atmospheric air, you need to bear in mind that you are talking about the presence of dry air as well as the vapor. Okay, so you need to know the partial pressure for dry air as well as the partial pressure for the water vapor. Okay. So just now is the enthalpy for air, and for the water vapor, okay, you can take the enthalpy reading, which is on the table at that particular temperature. The enthalpy at the vapor condition is the enthalpy for the water vapor. If you refer to the table, Okay, so there is a column called Hg and also the HL. So for the water vapor, we take the Hg as the enthalpy of the water vapor for that particular condition that we are doing the analysis and the calculation. Okay. As long as the temperature range is within -10 to 50 degree Celsius. So the enthalpy based on Hg, we can use that value because the area is quite negligible. Okay. So the enthalpy of water vapor in air can be taken to equal to the enthalpy of saturated vapor at the same temperature. So you refer to the table and you look at the temperature, and then you find the column of G, the Hg, F for liquid, G is for the vapor. So this is the enthalpy for the water vapor. And in this topic also, we going to use a lot of parameters, and then there are some parameters that you need to remember, not only the symbol but also the pronunciation or the name of it. So for example, here you're talking about alpha, beta, gamma, delta, epsilon, and then theta, phi, omega. Okay. So these are the common Greek alphabets that are being used in the thermodynamics. So why I talk about this, because when you write down your answer script, you need to write it clearly. For example, you're talking about gamma, you're talking about epsilon, then is it E or is it epsilon or is it number 3? So all of this has their own meaning, especially in the thermodynamics. Okay. For example, here omega, you're talking about the humidity, then the way you write your equation must be clear so that not to be confused with other parameters that you are dealing with. Okay. Okay, the next one, after we define the atmospheric air and also the dry air, we're talking about the specific and relative humidity of air. So the first parameter is what we call as the absolute or the specific humidity. Okay, this is number 1. And then number 2 is the term of saturated air. Number 3 is the relative humidity. Specific humidity or absolute or humidity ratio. So if you look here, you have 3 different terms or terminologies: absolute humidity, specific humidity, or humidity ratio. Okay. So when you have your questions or your tasks dealing with mixtures, if you been given the humidity ratio as the term that you need to analyze, then basically you're talking also about the specific humidity or the absolute humidity. By definition, is defined as the mass of water vapor present in a unit mass of dry air. It's the ratio between the mass of the vapor against the mass of the dry air. So the symbol is omega. It's not W, it's omega. A unit mass of water vapor, so 1 kilogram of water vapor divided by 1 kilogram of dry air. And then if you're applying the other gas behavior, we can then expand equation 1, then you can put it as the pressure terms. So 0.622 multiplied by the partial pressure of the vapor divided by the partial pressure of the air. And you rearrange, then you can get this next equation. So you have two options to define the specific humidity, okay, or the humidity ratio. Saturated air is conditions where the air is saturated with moisture. Okay. So the air initially zero water vapor, and then the presence of water vapor increasing over time, and the air is saturated with the water vapor, nearing the saturation point. So we call it as a saturated air. Saturated by the presence of water vapor. Kehadiran wap air hampir mencecah nilai ataupun kadar tepu. Udara tepu lah. Udara tepu merujuk kepada kehadiran wap air yang tinggi. The third parameter is the relative humidity, the ratio of the amount of moisture in the air holds. To the maximum amount of moisture the air can hold at the same temperature. So the ratio of the amount of moisture at that particular air that is holding against the on record based on experiment and on the previous analysis, what will be the amount of moisture that the air can hold at the same temperature. So the symbol is here is the symbol phi. Okay, so phi is relative humidity, the mass of moistures divided by the mass of moistures that the air is capable to hold at that particular working temperature. So the pressure that the air can hold, the maximum amount of moistures, is equivalent to the saturated pressure at the given temperature, because it's deal with the presence of saturated air and the high the presence of high content of water vapor. Okay, so these are the three parameters that you need to be aware of, and the symbol. So you need to use whatever strategies or formulas or tactic to remember the definitions. Okay, humidity ratio, omega, relative humidity, phi, and what will be the equation involved. And you can also try to combine them and rearrange so you can get this kind of relationship. In most practical applications, the amount of dry air in the air-water vapor mixtures remain constant, but the amount of water vapor changes. Okay. The only thing that change is the quantity of the water vapor, because the air is just like that. Unless you dealing with a vacuum, because air will be there, but what you can add and remove is the amount of water. So therefore, the enthalpy of atmospheric air is expressed per unit mass of dry air. It's not being expressed as per unit mass of water vapor, because because the air is what is remains there. Okay, because the value of dry air remains constant. So using this assumption, then you can work out the enthalpy for the atmospheric air. So it's defined by the enthalpy of the dry air as well as the humidity ratio and also the enthalpy of the water vapor. Okay. And then it follows the next terminology, the dry bulb temperature. The dry bulb temperature is the ordinary temperature of atmospheric air. And here the enthalpy of moist. So it's another way to describe the quality of the air. Either we say atmospheric air or call it as a moist air. So both carry the same definitions, which means there is a presence of water vapor in the air. Okay, so everything is expressed per unit mass of dry air, not per unit mass of moist air. Okay, the next thing to understand is the concept of dry bulb, wet bulb, and dew point temperatures. Why we use these three parameters? Because we want to define and determine the state of the humid air. Okay, sorry, panggil apa? Kelembapan, humidity, kelembapan, kehadiran buang air dalam udara sekitaran. The knowledge of only two of these values is enough to determine the state of the moist air. Okay, if we know two of the three, then we can determine the content of the water vapor, the energy, okay, based on the enthalpy reading of the air. For a given two types, the two units of thermometers of the same types, okay, so you can look at the bottom here. On the left is what you call the dry bulb. On the right is the wet bulb. The difference that for the wet bulb temperature, we purposely enclose the thermometer with we call it as the wet cloth. So that is the difference between dry bulb and wet bulb in terms of the physical things. So for the wet bulb, we physically trap a bit of moistures at the end of the thermometer, whereas the dry bulb is there's no insulation, there's no medium, and then the end of the thermometer just simply in contact with the incoming air. So the term dry bulbs, so when you write it down, make sure you put it as a dB subscript, or we call it as the air temperature. Basically the reading for the ambient air. Why we call it dry? Because the air temperature is indicated by thermometer, not affected by the moistures of the air. Okay, so you have the thermometer is simply exposed to the surrounding, whereas for the wet bulb we have a medium of a wet medium, so the thermometer cannot in contact with the surrounding air. Whereas for the dry bulb, the thermometer is simply exposed to the surrounding, freely exposed to the air but shielded from radiation and moistures. Okay, if there is no moistures at the under the surface of the thermometer, then we call it the dry bulb temperature. Why we measure the dry bulb temperature? Because this is indicator of heat content, and on the psychrometric chart, this is shown on the bottom axis, or if you are dealing with a molar diagram, it's along the left side of the molar diagram. Constant dry bulb temperature is on the psychrometric chart is the vertical lines, and on the molar diagram, the constant dry bulb temperature is the horizontal lines. So this is the psychrometric chart. Okay, so I'm not sure about this semester's final examination. Will there be questions that require you to use the psychrometric chart? But usually it's either this one or the cooling tower. So usually it's alternating. So this is psychrometric chart. So you can look on the horizontal axis. This is the dry bulb temperature reading. Okay, and then here is the barometric pressure, and then the moisture content. Okay, and then is the web up and the dew point temperatures. So those the vertical lines on the psychrometric charts are the dry bulb temperature reading. So these are the dry bulb yang menegak ni. Okay. Whereas for the molar diagram, another graphic representation of the relationship between air temperature, moistures, and enthalpy. And molar diagram is basically a variant of the psychrometric chart. So this is the molar diagram. Okay, so it's expressed in terms of pressure versus enthalpy. Okay, and then we have the entropy reading, and then also the temperature. So another way of describing the quality of the atmospheric air. Okay. Usually we refer to the psychrometric chart, especially if you are dealing with industries related to the air conditioning. But both are applicable in the industry. So really related to what your industries or company is using and what are the chart that they are much prefer to use. Okay, so wrap up, the thermometer is in contact with the dry air without any medium or without any interference, okay, to the air. Okay, the next thing is what we call as the wet bulb temperature. Another terminology is called as the adiabatic saturation temperature. The difference with the dry bulb that we enclose the thermometer with a wet muslin, basically a lightweight cotton cloth. Okay, so you put this cotton cloth is wet, you dip into the water, and then you wrap the thermometer, so you have your wet bulb temperature. The adiabatic operation of water from the thermometer bulb and the cooling effect is indicated by the wet bulb temperature. The wet bulb temperature, is lower than the wet bulb reading. The rate of evaporation from the wet bandage on the bulb and the temperature difference between the dry bulb and the wet bulb depends on the humidity of the air. Okay. Kadar penjejatan air daripada selaput yang basah bergantung kepada kadar kelembapan sekitaran. It really depends on the humidity of the air. The evaporation for the wet cloth is reduced when air contains more water vapor. If the surrounding air, the atmospheric air, contains very high amount of water vapor, then the wet cloth, okay, it cannot evaporate as fast in comparison if the atmospheric air is nearing the dry air conditions. Okay, so udara kering lagi cepat untuk dia menyejat. Udara yang lembab disebabkan oleh kehadiran kandungan air yang tinggi, air yang ada di selaput yang basah tu sukar untuk menyejat ke sekitaran. So that's why we use the concept to gauge or to estimate the presence of humidity in the air. The wet bulb temperature is always between the dry bulb value and also the dew point. So if you put it as a scale, you have the dry bulb, okay, and then you have the wet bulb, and also the dew point temperature. Okay, so there's the positions of the different temperature. And for the wet bulb, there's a dynamic equilibrium between heat gain. Because if the wet bulb is cooler than surrounding, so there is a heat gain or heat loss because of evaporation. Okay. The wet bulb temperature is the temperature of the object through evaporative cooling. Okay, because of the evaporation process of the moistures from the enclosure from the wet cloth. So when we combine the readings from dry bulb thermometers and also the wet bulb thermometer, we can get the temperatures that we can then transfer on to the circumference chart, and from there we can estimate or determine what is the state of the humidity for that particular volume under investigation. Lines of constant wet bulb temperatures run diagonally from the upper left to the lower right on the psychrometric chart. Okay, the next one is the dew point temperature. Temperature where the water vapor starts to condense. Okay, because we have the condition of what we call the saturation condition or the saturated air condition. Okay, so this condition is where the water vapor is increasing until the saturated air reaches the temperature where the water vapor is ready to condense. Okay. The amount you witness or observe the presence of water vapor, as I mean the presence of water as liquid, okay, it shows that that particular atmospheric air already reached the dew point temperature.